on-call.
How are we doing with this? Is this good? All right. So, a reminder of where we are. Last time we started talking about ACID transactions, and you will remember that ACID is an acronym, just sort of a mnemonic device, really. We set aside the C of consistency, which was sort of extra. C is easy. C is just there are integrity constraints in your database, and before you commit, make sure they're all true. And if they're false, then abort the transaction. So that's consistency. We'll just make sure the database respects integrity constraints. Take that off the table. A and D, atomicity and durability, are going to go together. Atomicity says the transaction all happens or it doesn't happen. Durability says if it all happens, then it all happens durably. It happens forever, okay? More particularly, when the transaction tells the application level, when the database tells the application level, the transaction has committed, that's a promise, all right? And that transaction will be durable. A and D will be the topic of next week's lectures on recovery. That's the mechanism we'll use to enforce atomicity and durability. Today, though, we're going to talk about isolation. We started last time, and we'll continue forward. Okay, so isolation is the mechanisms for isolation are mechanisms of concurrency control, mechanisms to control the degree of concurrency across transactions. So database systems are going to allow transactions to interleave the actions of many transactions. So an action from the database's perspective is a read or a write of an object. We're going to ensure that they do not interfere in a specific sense. Okay? Now, particularly, we're going to define serial schedules. That is to say, schedules where each transaction runs in isolation, one at a time in an order, as being our touchstone of correctness. And we're going to define what schedules are equivalent to serial schedules. All right, we started this last time. So the definition of a serial schedule, formally, is that every transaction is a string of reads and writes. It runs from start to finish without any intervening actions from other transactions. Second definition is that two schedules are equivalent if they involve the same actions of the same transactions. All right, so it's the same bucket of activity, and they leave the database in the same final state. All right. We will not concern ourselves with output in this discussion. However, if you want to model output, you can always write your output to a table before you send it to the screen. And then all this formalism will capture output as well. So you don't really have to write your output to a table. You can just pretend you're writing it to a table and do your analysis, your serializability analysis that way. Okay, so just imagine that any output or any real-world activity is captured as writes to the database, and then all our mechanisms will work. Okay, well, we'll come back to that idea when we talk about recovery. The one caveat to that is it's really hard to roll back work you've done in the real world, right? You can't unfire the missiles. You can't get the money back into the ATM machine after you spit it out, right? Stuff like that. So you do have to be a little bit careful with the real world. Some of the real world is not invertible. Okay, so when we talk about recovery and undo, we may have to be a little careful about the real world. That's a topic for next week. All right, finally, given that we say serial schedules are good, and we say that two schedules are equivalent if they leave the database in the same state, we can define serializable schedules as the schedules that are equivalent to some serial schedule. Doesn't matter which serial schedule, it's serializable if there's some ordering of the transactions that gets the same output for the same actions as this schedule. All right. This is a nice idea, right? It captures some definition of truth, and it's going to give us a framework to define what's good and what's bad, right? And that was really hard to do when you're thinking about parallelism and concurrency. And I would say one of the really nice things about the transactional model is it gives us a strong definition of correctness. A lot of times when you're writing multi-threaded programs or you're thinking about parallelism or concurrency, it's actually pretty hard to get people to specify what's the space of correct behaviors and what's the space of incorrect behaviors. Serializability is one reasonable definition for correct behaviors. And prior to its definition, people tended to think very sort of narrowly about, well, what reads and writes should I worry about? This is very clear, okay? Serial schedules are understandable. So let's just do things that are equivalent to serial schedules. With that, though, we have to actually turn this into code, right? So it's nice to say that schedules are equivalent to serial schedules, but how do we guarantee that in a system? Well, to get an easier check, we're actually going to narrow our focus a little bit. And we're going to just use the notion of what operations conflict with each other and what operations don't conflict. And again, we're going to do this at a very low level at the storage manager interface. So we're just going to think about reads and writes. So we'll say that two operations in this API of reads and writes conflict if they are from different transactions, they are on the same object, and at least one of them is a write. So two reads don't conflict with each other by this definition, which sort of makes sense, right? A read and a write conflict, and a write conflict, all right, if they're coming from two different transactions. We're going to assume, by the way, throughout this, that each individual transaction is running in serial. So there's no parallelism within a transaction, no intra-transaction parallelism, okay? So don't get your head spun up about how do we do things in parallel in a transaction. We'll figure that out. We won't figure that out. We're just going to take it as a given that transactional updates in particular are going to happen in sequential order per transaction, okay? So we won't have to worry about parallelism inside a transaction. Okay, now here's another definition. Unfortunately, one of the ways you deal with all this stuff is you very carefully define what's correct, and you get definitions that are actionable. So here's a somewhat narrower definition than serializability. It's called conflict serializability. All right, and the definition goes like this. Two schedules, it's the same structure of definition. First, we're going to define equivalence of schedules, and then we're going to define serializability as equivalence to a serial schedule. So two schedules are conflict equivalent, if and only if, so it's a definition. They involve the same actions of the same transactions, and every pair of conflicting actions is ordered the same way in both the two schedules. So if the first schedule had transaction 1 writing A before transaction 2 read A, then the second schedule would also have transaction 1 writing A before transaction 2 reads A. So all the conflicting actions are ordered the same. The non-conflicting actions, reorder them any way you want. They don't conflict, so it's fine. Okay, so we'll say that two things are conflict equivalent if the only differences between them are non-conflicting orders of actions. And you'll see visually an example of this, I think, on the next slide. It'll make it very obvious. So given that two schedules are conflict equivalent, we can say that a schedule is conflict serializable if it's conflict equivalent to some serial schedule. All right? Now, this is something we're actually going to be able to enforce or test at the implementation boundary because this is just the definition with regard to reads and writes. Right? We'll be able to look at individual reads and writes and reason about them. What I'll say, though, is that it's a narrower definition than the serializable schedule. So there are serializable schedules we would be happy to have that are not conflict serializable. So if we lock our system down and say we're only going to do conflict serializable, there are some good schedules that we're not going to get. So we're going to look at them and go, gee, that looks dangerous to me. Let's not let that happen, even though it would have been fine. All right, so conflict serializability is conservative. It's a little too careful. It's cautious, all right, but it's correct. Right? And it's enforceable, as you'll see. All right, and the reason we did it is because it's kind of something you can actually implement. Let's look at an example. So a schedule S is conflict serializable if, another way to say this is you can transform S into a serial schedule by swapping non-conflicting operations. If you can kind of bubble sort the stuff that is out of order without violating the conflict rules, keeping all our conflicts in the same order, then everything's going to be okay. So here's an example. There's two schedules, there's two transactions, I think, going on in this picture. What is going on in this picture? This picture is weird. I think this picture animated wrong. There we go. Okay. So in the top, these are two copies of the same schedule, all right? And one of them we're going to keep there so we can use it for reference, and the other one we're going to play with. So on the top in the gray box, we're going to keep that one fixed, all right? And it's a schedule. Each transaction is horizontal. So transaction 1 is line 1 of this gray box, and transaction 2 is line 2. Transaction 1 is in red. Transaction 2 is in green, all right? And transaction 1 is interleaved, obviously, with transaction 2. So entirely within the box, time goes from left to right. First, transaction 1 reads A, and then it writes A. And then transaction 2 reads A and writes A. Transaction 1 then reads B and writes B. And transaction 2 then reads B and writes B. Okay? This is sometimes called a schedule. This sort of timeline of history is called a transaction schedule. All right? And so what we're going to do is we made a copy of that schedule on the bottom, but now we're going to start messing with it and seeing if we can reorder it without breaking any conflict orderings to get to a serial schedule. So let's have a look at this. That write of A at the bottom and that read of B above it. What we want to do is move all the red stuff to the left. Let's see if we can find a way to move all the red stuff to be consecutive without violating conflicts. So let's look at this. That red R of B, can we swap the order with the right of A without changing the conflict ordering? Does R of B and W of A conflict? No, because they're on different objects. They are from different transactions. One of them is a write, but they're on different objects, so they don't conflict. In fact, they have nothing to do with each other, right? One's on A, one's on B. Who cares? So we can swap those. Those are still equivalent schedules, right? Because they're conflict equivalent. We only change things that are non-conflicting. What about the read of B and the read of A? Can we swap those? Yeah, again, two reads don't conflict. Okay, we're starting to get more of our red stuff together. What about the write of B and the write of A? Can we swap those? Again, yes, we can because they're non-conflicting. They're on two different objects, right? So that's fine. And again, the write of B and the read of A, non-conflicting. So what did we do? We changed around the order of the actions individually. None of them changed the conflict ordering, which means that every step of the way we were generating something that was conflict equivalent to the original schedule. And in the end, we got a serial schedule, right? So clearly, the original schedule was conflict serializable. Make sense? Okay, so that's the game. I mean, it's sort of like bubble sort with this rule about conflict serializability or conflict ordering. Here's another example. Read of A, and then read of A, write of A, and then write of A. Is this conflict serializable or not? Well, let's try to move the red W to the left. Can we swap that red write of A with the green write of A? No. Two different transactions, same object, one of them is a write. Both of them are writes. So they are in conflict with each other. We can't reorder them. So we can't make the red transaction happen before the green transaction and get the same outcome. All right, let's try the other direction around. Let's try to do green first and red second. Can we move the read of A before the other read of A? Yes. So that green read of A can move left. What about moving the write of A before the red read of A? Can't do that either because there's two different transactions, same object, one of them's a write. So we can't move the green before the red. We can't move the red before the green, which means there is no serial schedule that is conflict equivalent to that schedule. This is not conflict serializable. This is, in fact, a kind of a mess. All right? And when you think about it, it sort of makes sense that it's a mess. It's like the red transaction did a read on A, and then the green transaction kind of shot in there and changed the world, and then the red transaction is going to do a write. And, who knows what the green guy intended, but it's kind of gone. Right? It's not as if green went first and red went second. It's just some weird interleaving. Okay, so this is not serializable, or it's not conflict serializable, importantly. And in fact, this is worth fixing in the slides. I'm just going to take a minute, and I will, I think, upload a new copy of these slides because I changed a couple bugs with the animation too. So it is not conflict serializable. All right. So here's a somewhat more simple way to kind of capture conflict serializability. We're going to draw a graph, and this graph is going to very easily let us test for conflict serializability in any schedule. And the way this graph works, it's going to be called a dependency graph, is there's going to be a node per transaction. Okay? And there's going to be an edge from transaction I to transaction J if some operation, a read or a write, of Ti conflicts with an operation of Tj. And that operation from Ti came first in the schedule, came earlier in order. So the direction of the edges is with respect to time. An edge from tail to head is previous in time to later in time. Okay? And there's a theorem which is very straightforward that says schedules are conflict serializable if and only if the dependency graph is cyclic. And it's exactly through those movements. You can prove it basically by trying to do the induction on those little movements we just did. You can't move those guys around to be serial if there's a cycle in this dependency graph. You'll run into yourself, so to speak. You'll run into a conflict. But if you can do it, then this schedule will, this graph will be cyclic. It's an easy thing to prove. I encourage you to do it on your spare time just for fun. All right. But that's an easy test. You can always build one of these conflict graphs from your schedule and then just test the graph for cycles. How do you test a graph for cycles? Just use your favorite traversal algorithm, right? Search algorithm, and see if you revisit yourself. Yeah? If you can reach yourself, if any node can reach itself via traversal, then it has cycles. And if you manage to traverse the whole tree without visiting anything twice, then no cycles. Right? So use BFS or DFS or what have you. Okay. So here's an example of a schedule that's not conflict serializable. We're going to build it as we go and build the dependency graph as we go. So we have two transactions, T1 and T2, and so far they have no dependencies. That is to say, no conflicts. If we make T2 read A, that means that T1 conflicts with T2, and T1 went first with its right of A. Yeah? So the right of A, read of A pair is a conflict, and T1 came first in time. And now suppose T2 has a bunch of other activities, like it does another write on A, which just only reinforces that edge. It reads B, it writes B, and then T2 reads B. Well, now we get an edge in the other direction because of the write of B in T2 came before the read of B in T1, right? And so this thing has a cycle, and because it has a cycle, the output of T1 depends on T2, the output of T2 depends on T1, and there's no way to serialize this schedule of transactions without breaking conflicts. Yes?
So in your previous example, where we couldn't serialize, conflict serialize task 1, task 2, because we moved the read over, we couldn't move the write over in either direction. So would that mean T1 is dependent on T2 and T2 is dependent on T1, and they're both A?
Yeah, let's look at this example, right?
Yeah.
So let's just draw it. This is a sort of a smaller version of what we just had in the following slide. So we've got the first row is T1 and the second row is T2. Okay? So we can just march down this schedule and we say that, look, the read of A and the read of A don't conflict, but that write of A, the third item in the list, conflicts with the read of A, and which means that T1 conflicts with T2 like that. And then similarly, that write of A at the top right conflicts with the write of A below it. So you get something like that. Okay? And so we just get a cycle from those dependencies, from those conflict dependencies. All right. Okay. Before we go on, a technical topic. So, this is sort of one of these things where you start to realize this thing gets deeper than you might have guessed. This is what's called view serializability. It's another definition of serializability. It's not conflict serializability. It's not general serializability. It's view serializability. And I'm going to define it, and it's going to be a lot of words, but at the end of it, you're going to go, oh, that makes sense. That's a good definition. But it's different. And so, like, at some point, you got to kind of choose your poison. You got to pick which one of these things you think is the one that is most intuitive and makes most sense to you. So here's a definition called view serializability. Here we go. Two schedules, S1 and S2. Remember, a schedule is that string of interleaved actions, right? These two schedules are view equivalent. It's a different kind of equivalent. Same setup, right? If they have the same initial reads. So every transaction reads the same stuff. So if Ti reads the initial value of A, nobody's ever written it in Schedule 1, then Ti also reads the initial value of A in Schedule 2. All right? So if in the first schedule Ti reads an unpolluted value of A, then in the second schedule it also reads an unpolluted value of A. They also have the same dependent reads. So by contrast, if Ti reads a value of A that was written by Tj in the first schedule, then it reads a value of A written by Tj in the second schedule. All right? So if you want to think about data being sort of passed along from one transaction to the next, the way the data is passed along is the same. Either you read unpolluted data or you read data written by the same guy you read from in the other schedule. So all the reads are kind of the same. And then the writes have the same winners. So if you have some variable A, the last writer in the first schedule is also the last writer in the second schedule. So think about the state of the database at the end. Everybody read the same stuff, and the same writers won. So, like, that's everything, right? I mean, anything else is kind of transient. Seems like a perfectly reasonable definition, right? It's not actually the same as conflict serializability in a fussy, detailed sort of way. And basically, it is conflict serializability, but it's a little more relaxed. It allows what are called blind writes as well. So I'll give you an example. Here's a transaction schedule on the left. It's got 3 transactions, T1, T2, and T3. In the first one, T1 reads the clean value of A, T2 writes A, then T1 writes A, and then T3 writes A. Okay, let's see. T2 read T1 read the clean value of A, right? So we got to make sure that in the next schedule, T1 also reads the clean value of A. And T3 is the winner on the right of A. So we got to make sure that's true also. So let's look over here. T1 reads A and writes A, and then T2 writes A, and T3 writes A. All right, clearly these are not conflict equivalent because we swapped two writes on the same object from two different transactions. All right? But in this case, the reads are the same, and the winning write is the same. T3 wins in both cases. Doesn't matter what order the writes of T1 and T2 happened in. Doesn't affect anybody. Kind of weird, right? So these are called blind writes. It turns out, well, the reason they're called blind writes is notice that both T2 and T3 write A without ever having read them. So they have no idea what's in A. They're just overwriting it. It's called a blind write. Okay? And there's actually a proof that says that the only schedules that view serializability allows that are not conflict serializable are ones with blind writes. So in essence, view serializability is a little more relaxed than conflict serializability because it allows these crazy blind writes. All right? It's a pretty natural definition, actually, view serializability. All right? Unfortunately, it's harder to implement, so people don't do it. Question?
What if two different transactions write on the same object?
Okay, two different transactions write on the same object. We're talking about view serializability. What's the question? Well, if the two transactions write the same object, but in both schedules the same writer goes last, then everybody read the same stuff as well, which is the definition of view serializability. Then the writes that people choose to write will be the same because they read the same stuff. Everybody read the same things before their writes. And the last writer is the same, so the remaining value in the database is the same. Yeah? Nobody essentially is fed different information. Everybody consumes the same information in both schedules because they have the same reads. And the output of the database has the same writes. So it seems like it's good. It's just a little harder to enforce than conflict serializability, it turns out. And the difference, it turns out, and this is the part which is very interesting, I think, is that the only difference is handling these blind writes. So if you go with conflict serializability, you can't identify that some of these blind writes are going to kind of make things work out. T3 is going to wipe out all the stuff before it anyway, so don't even worry about the stuff before it at some level. We're not going to get that level of intuition from conflict serializability, but that's okay. Notice, sort of what's going on. I mean, another way to look at this example is this right here makes the ordering of those two writes irrelevant. Doesn't matter what order these guys write A. This guy's going to clobber them anyhow, right? So conflict serializability can't see that. It's being real careful about those previous writes, even though no one will ever eventually see them. Okay. Now, without blind writes, T3, if there's no blind writes, that means it has to read A before it writes A. And probably that read maybe would happen here, and then things would be different. Okay. And then it wouldn't be view serializable anymore if you change the order of the writes before it. Make sense? Okay. So much for view serializability. It's a bit of a curiosity because it's hard to implement, and mostly what people implement is conflict serializability. But what I will say is that there's been a lot of innovation in the last 5 years maybe because of big data and NoSQL and things like that. People have been inventing a lot of new protocols for implementing transactions or things kind of like transactions, serializability. And there's been a lot of innovation. So you may want to keep this in your back pocket as an interesting fact that maybe you'll exploit someday in a new design. All right? One of the reasons, by the way, for the changes in these protocols and the reason people are inventing new ones has to do with changes in hardware. So because we have computers that are spread all over the world, for one thing, we have very high latencies for writes. Right? Some writes, if you're going across the globe, the speed of light slows them down a lot. Right? On the flip side, in many cases, we're not using magnetic disks, which means that you can make up new concurrency control protocols and things that don't worry about seek costs and stuff like that, and may make different decisions about when to lock things and how to lock things, and whether it's better to do locking or better to do multiple versions of data. So we'll talk about some of this hopefully next Tuesday. We'll do a little bit of an advanced lecture on concurrency control, but basically some of the reason that your generation of folks are revisiting this stuff is because the world has changed from a hardware perspective, and it's worth rethinking a whole bunch of these techniques that I'm going to teach you. All right? So these are kind of the classical techniques we're going to do today, and at least with the classical techniques, view serializability is hard to enforce. Okay. And remember that neither of these is all of serializability. Each of them is a subset of serializable schedules because they don't understand the meanings of the operations in the data. So let me give you sort of a concrete example of something that's serializable, but you wouldn't know it. So suppose that we knew that in our banking application, we had a banking application, okay? But every morning at 9 o'clock, everybody's account is reset to $100. Why? Well, I don't know. Maybe it's a game. Maybe it's a simulation. Maybe it's not really banking, okay? But 9 o'clock every morning, everybody's account is $100, which sort of means that, at least from the perspective of 9 o'clock in the morning, it doesn't really matter what happened yesterday, right? You could have things happen in any old order yesterday. It'll still lead to 9 o'clock in the morning, it's $100, okay? So from a certain perspective, at least if you turn off the system at 9 o'clock the next morning, it's serializable no matter what happened yesterday because it gets the same outcome of the database no matter what order things happened in. How do you know that? Well, because you know that's how you implemented the code. Right? It's a high level of semantics. You can't learn it from the reads and writes. This is just a database where at the end, when you turn it off, everything's $100. The end of the transactions. All right, so that's a little crazy, but it would be serializable, and it would not be any of these other kinds of serializable. It wouldn't be conflict or view serializable. All right, it has to do with our understanding of how the system works. Okay. So as we said, so last bullet, in practice, conflict serializability is what gets used because it can be enforced efficiently. There are actually some things you can do beyond conflict serializability that are done commonly. Well, a common example of it is escrow transactions, which I won't get into here. But that's a case where a certain amount of semantics is baked into the concurrency control policy. And just to give you the flavor, escrow transactions reason about increments and decrements. So the classic example is bank accounts. If you deposit $1,000 and withdraw $200, the net total is that you've added $800 to your account. And it kind of doesn't matter what order you do them in, as long as your account balance doesn't go below zero. And in some countries, actually, it's okay for your account balance to go below zero for a little while. So escrow transactions basically allow you to reorder increments and decrements or similar things like that within certain safety bounds. And that takes into account certain semantics, the semantics of integers and addition. Okay? So it's one example where some semantics have been pushed down into the concurrency control layer. All right. Just an aside. Okay, so now we've got serializability definitions, and I have asserted to you that we can implement something like conflict serializability, but I haven't told you how to do it. So now's the time to go from theory to practice, okay? And by the way, this was all done by the same folks. So all the definitions of serializability and transactions and all that good stuff were done by Jim Gray and his friends at IBM. And the implementations I'm going to show you next were also done by Jim Gray and his friends down at IBM. And they were all implemented in a system you've heard of already called System R, which also had the query optimizer that we learned. Right, so it was a pretty influential system. Okay, so the technique we're going to describe now is called two-phase locking. Not to be confused with something called two-phase commit, which we may learn next week, but it's also a database thing. This is two-phase locking, all right? So keep that in mind, 2PL. It is the most common scheme for enforcing conflict serializability, even though it's sometimes negatively described as being pessimistic, all right? And sometimes people want to implement an optimistic concurrency control policy, which would be more cheerful. But we're going to implement locking, which is a pessimistic policy. And the idea is that when you're going to change something or even read something, you're going to set a lock on it to avoid any possible conflict that could happen because of your actions. So in advance of doing something, you'll set a lock. Now, other schemes might optimistically just let you do stuff, maybe even let two people do things that you might think will conflict and just let them keep going forward. And maybe later on, we'll check to see if anything bad happened. All right, so that's a kind of more optimistic scheme. We're not going to do that today. Maybe on Tuesday if we have time of next week. But today we're going to look at these pessimistic schemes that will prevent any conflicts from happening in ambiguous orders. Okay, so here are the rules for our locking scheme. And locking, when I first learned about locking in college, I thought it was some kind of computer magic, right? Like maybe it's done in hardware, or maybe it's like electronics implement locking. It's not like that at all. Locking is just a protocol. It's a software convention, And we're going to make sure that everyone obeys this protocol by being everyone. That is to say, we're implementing the transactions, we're implementing the queries, we're implementing the database. We'll just make sure that they follow these rules. Okay? If you somehow had a database system that was like peer-to-peer database system, then you would need a locking protocol that was a public protocol where people would like send messages to request locks somehow out in the world. But that's not what's happening here. What's happening here is this is all implemented by us for our system. The user doesn't see any of this. This is all under the covers of our database system. And we're just going to follow this protocol slavishly in our code. So here are the rules we're going to implement across transactions in our system. Before reading an object, a transaction must obtain an S, or shared, lock on that object. And before writing an object, a transaction must obtain an X, or exclusive, lock on that object. And X cannot get new locks after it releases any of its locks. That's the two-phase part. So the first part is the locking part, the first line, the black line, which is when do you have to get locks? Well, you have to get S locks before reads and X locks before writes. And the two-phase part is there's a phase where you're acquiring locks, and then there's a phase where you're releasing locks. And you can't go back. Okay? Once you start releasing locks, you can never acquire locks again. So those are the two phases. And when you look at those two phases, you can draw a little graph for a transaction over time as to the number of locks it holds. Right? It's got an acquisition phase and a release phase, and that's it. And sometimes that point where you start releasing is called the lock point of the transaction. That's the most locks you ever had. And at that point, every object that you touch, you have a lock on that object. And in some sense, at the lock point, you've frozen the database, all the parts of the database that you care about, and you've got them under your control. And of course, you can do your own thing because no one else can get them because they are locked, right? So at that lock point, you really almost have achieved what you wanted, which is total control of the database. It's just for those things that you care about, right? All right, so two-phase locking guarantees conflict serializability for pretty obvious reasons, because you don't do those reads and writes unless you're the only person who's, two conflicting actions, like a read and a write, will not happen in order because of the locks that you have to set, okay? So any conflicts between two transactions will be totally ordered based on the lock protocol. Unfortunately, there is something bad that two-phase locking does not prevent, which is what's called cascading aborts. So before we go into cascading aborts, let's take a minute and make sure we believe that two-phase locking guarantees conflict serializability. Let's think about this for a second. Suppose that we had transaction 1 requesting, let's say we have two different transactions. Let's just make this really simple. T1 wants to read A, and it wants to write A. And T2 comes along, and it wants to do the same thing. It also wants to read A, and it wants to write A. All right? One thing we didn't spend any time on, which we should do on the previous slide, is the lock compatibility matrix. So if T1 has a shared lock on some attribute A, T2 can also get a shared lock on A. So two shared locks are compatible. Two different transactions can have a shared lock on the same object. That's why it's called a shared lock. Yeah? Okay. An exclusive lock, however, is not compatible with anything. So if I have an exclusive lock on something, you can't have any kind of lock on that something. Okay? That's why it's called exclusive. All right. So let's see what happens with our little serializability scheme here with two-phase locking. So suppose that T1 gets a read lock on A first. All right, so what's going to happen is this is the desires of the two transactions. Here's the actual schedule and time. So T1 wants to read A. So it's actually going to have a shared lock on A now. So if you imagine A as an object on the database, T1 has a shared lock on A right now. All right, that's nice. What would you guys like to happen next? Various things could happen next. Which one of the remaining three actions shall we do next? Yes? Okay, let's let this action go next. In which case, T1 has to upgrade its lock to exclusive, which is fine. It can upgrade from shared to exclusive because there's no other shared locks right now anyway, so it gets the exclusive lock. And it does its write of A. All right. And now we'd like to do T2. Can T2 run? It's read of A. It's going to request a shared lock, but it's not going to get it because this has got it exclusively locked. So T2 is hanging around A, kind of like a moth around a flame, trying to get in there. It would like to have a shared lock. When will it get a shared lock? When T1 relinquishes its lock, after which it can acquire no more locks, mind you, right? So once T1 lets go of this lock, which, by the way, was the only lock T1 held, then T2 can go in and get its shared lock and do its read of A. And then, of course, it can upgrade to an exclusive and do its write of A. All right, this was clearly a serial schedule. I will let you do the homework of realizing that any other schedule you do will also be serial. But let's do one more example. In the other example, we'll still let T1 go first. Let's change this around a little bit. T1's going to get its read lock of A, but now, rather than the suggestion we had before, let's suppose we're here, that this goes next. T2 requests a read lock, or a shared lock on A. Is it compatible with T1? You bet it is, because it's shared. So we'll say T2 and T1 have shared locks on A. And so the next thing that happens is a read of A. All right, now what shall go next? It sort of doesn't matter because they're symmetric transactions. So let's let T1 request its exclusive lock on A. All right, T1 wants an exclusive lock on A. Can it get it? It cannot. Okay, so it waits around. T1 is waiting around for an exclusive lock. And so T2 maybe will get scheduled, and it wants an exclusive lock on A. Can it get it? It also can't get it. So this is a bad situation. Now, this is what's called a deadlock. Because T1 is waiting for T2, and T2 is waiting for T1. Now, we're going to talk about deadlock on the very next slide, in this exact case. But just let's make this simple. Suppose that our solution to deadlock was to say, heck, if nobody can go forward, let's shoot T1 in the head. It's going to release its locks, and then T2 can go, right? And so this won't have happened because it got undone by shooting T1 in the head. And T2 is going to go first. And then T1 will get rescheduled to run again, and T1 will go second. All right, so we will get a serial schedule. T2 will go before T1 because T1 had to restart. All right, and you can prove to yourself that no matter how you interleave these things with two-phase locking now, we've done essentially all the cases. The rest of them are symmetric. One of these transactions essentially will go before the other because of the locking protocol. All right, it's not only that... in this case, obviously, all their actions are conflicting because they're all on A. If some of them had been non-conflicting, like T1 was dealing with B and T2 was dealing with C, those could have been reordered, right? And that's exactly why two-phase locking kind of gets you the same effect as conflict serializability. If you lock two completely different things, then the order of those locks doesn't affect who goes first the way you would want because they're non-conflicting. And if you lock the same thing, you get totally ordered by the locking protocol. All right. So we'll talk about more about deadlock in a sec, but first let's talk about cascading aborts. So 2PL does guarantee conflict serializability, but there's this thing called cascading aborts. So it's a pretty straightforward thing to understand. Let's look at an example. The problem is that when you abort one transaction, you have to abort other transactions as well. That's why it's called cascading aborts. So look at this. T1 reads A and writes A. T2 reads A and writes A. Note that what T2 has this is the value that T1 wrote, right? And this could happen, this is a little dodgy. Remember, it's two-phase locking. So we have to assume that we didn't write down where the lock acquisitions happened here, but we're going to have to assume that if T2 read A, that means that T1 let go of its shared lock on A, right? Which means T1 can't acquire those locks on B where it's doing its reads and writes. It must have acquired those locks on B in advance of T2. All right, so this is actually a bad example, and I think the best thing to do is to not stare at it very carefully, and I'll fix it for next time. I apologize. I don't like this example at all. Because remember, two-phase locking, right? You have to release, once you release one lock, you have to release all your locks. I'm sorry, once you release one lock, you can never acquire new ones. And look, T1 clearly released its lock on A because T2 was able to read it, which means that those locks on B that T1 had, this all could have happened. It's legal, but it means it had to acquire those locks on B somewhere over on the left before T2 read A. Okay, and that I should have put that in the schedule somehow so that you saw that. Otherwise, it doesn't really make sense. So the way to fix this is to say, where's my mouse? Oh, by the way, T1 is acquiring locks on B here. One way to do that would be to have T1 read B and write B here, and then do it again there. That'd be okay. That'd be legal then, and you'd see that. But at this point, it's released a lock on A so that this guy can go, all right? And it already had locks on B, so it can continue here. Given all that, when T1 aborts, notice what's happened. T2 read a value that T1 wrote, because T1 was in the downswing of this release phase. T1 was starting to release locks, so there was a value, A, that it had released the locks for. T2 picked up that value, right? And now we abort T1 when it's halfway done releasing its locks. T2 read its dirty data. And T2's now read stuff that we're going to undo. We're going to abort. So T2 has to abort also, right? Because you can't let it go forward based on data that doesn't exist. All right, so that's the cascading aborts problem, and it's really easy to fix. Instead of having two-phase locking, we're going to have strict two-phase locking. And in strict two-phase locking, it's the same as two-phase locking, but the minute you release one lock, you release all your locks. So you release all your locks at once at commit time or at abort time. And you get a conflict graph that looks, lock graph that looks like this. You acquire locks, and then you release all of them. So there's no way for somebody to read your dirty data, because your data is either committed or it's aborted, and otherwise it's invisible. It's locked. Okay? So that's strict two-phase locking. Strict two-phase locking gives you conflict serializability without cascading aborts. And so that's what most people implement, is strict two-phase locking. Okay? With that, I thought it'd be worth going through some concrete examples in the slides, and we'll do them together. I think, let's look at these things. We'll talk them through. Okay. So this is not a two-phase locking schedule. This is just a schedule, some old schedule. And now instead of going horizontally across the board, we're going down the screen. Okay? And this is pretty typical in these transaction schedules, actually, to write them vertically, because most pages are oriented vertically. All right, so T1 is on the left, T2 is on the right, and time is going down the board. And so we're going to start out, and A is going to equal 1,000, and B is going to equal 2,000, and we want to know what the output is. And so I'm going to play scribe here on the board. Actually, somebody volunteer to play scribe on the board? It's not hard. Hold on, we haven't got there yet. I'm still looking for a volunteer. Was that a volunteer I heard? All right, come on. I can stand on the side. All right, we're going to need an A value, a B value, and an output value. I think. Yeah. That's not going to work. Okay, right, nice and big. Okay, so the first thing we're going to do is T1 is going to get an exclusive lock on A, and it's going to read A. Oh, A starts out at 1,000, and B starts out at 2,000. Will you put those in? Sure, that's great. Make sure to write real big. So T1 has an X lock on A. So you could say X of A under T1 if you want. Great. It reads A, so what does it think A is? Oh, that's the output. Don't write there. That's what we're going to print. You can move it. You can erase it and move it, but it goes in its own private memory. So maybe move T2 because they're really close to each other. Yeah, and then T1 is now going to have a belief about A. T1 thinks A is what? Because it did a read of A. It thinks A equals 1,000. And now T1 is going to decrement A by 50. A equals A minus 50. So now T1 thinks that A equals 950. And now T1 is going to write A back to the database. For reals. Yep. And it's going to unlock it. Oh, oops, we left out something. We left out in step 3 that T2 got a shared lock on A. How? I don't know. It's not two-phase locking. This is crazy locking, okay? So T2 has a shared lock on A. Why? I don't know. It just does. This is a buggy implementation. Okay, so now we're now at line 1, 2, 3, 4, 5. We've just written A back to the database, and we unlock A and T1. Okay, and now T2 is going to read A, and it gets what value for A? It believes A is 950. And it unlocks A, and it gets a shared lock on B, which is kind of irrelevant because we're ignoring locks clearly. The next thing that happens is T1 gets an exclusive lock on B. Okay, that's crazy, but let's say it happens. Now T2 reads B, and it believes that B is what? 2,000. And then it unlocks B, and then it prints A plus B, and that's what goes in the output. Okay, 2,950. Okay, now T1 reads B from the database. It increments it by 50 and writes it back. $20.50, and it writes it back to the database. And it unlocks B, and we're done. All right, and T1 and T2 both erase their main memory state. And what we have left is that the database has 950 for A, 2050 for B, and an output of 2950. All right, that is crazy because we didn't respect serializability in any interesting way. Was money preserved here? We used to have $3,000. We subtracted 50 from A, and we added 50 to B. Did it work out? Well, the bank worked out. The output didn't really make any sense, right? According to what we printed on screen, we lost $50 somewhere, right? Somewhere between the transfer, debit from savings and transfer to checking, it looks like we lost $50. At least that's what we printed on screen. It's not true, all right? And that's because we didn't respect serializability. Okay. So that was a little weird. Stay there. Maybe, would somebody else like to be scribe? It's really fun. You're doing a really good job. You're welcome. So erase the next board. Let's do the next one. All right, now we're going to do two-phase locking, and everything's going to be joyous. All right, and we're going to try to do it in the same order, but things are going to get held up waiting for locks. So the first thing that happens is T1 exclusively locks A. Yeah, you can do it on that board. That's fine. We'll all remember what happened. T1 exclusively locked A. But set up our initial conditions right, 1,000, 2,000. It's checking and savings, huh? And it reads A, so it gets 1,000. T2 requests a shared lock on A, but does not get it yet. So it's waiting, right, for that shared lock on A. So it's just waiting. W. Nice. It's spinning its wheels, doing nothing. Meanwhile, we've got to decrement 50 from A at T1. We are going to write A back to the database. And because T2 is just spinning anyway, T1 gets to keep going, and it's going to get an exclusive lock on B. And it's going to unlock A. All right, from now on, it can't lock anything ever again because it just unlocked something, right? It's two-phase locking. All right, it unlocked A. So no more locks for B, or for transaction 1, sorry. But it still has a lock on B, so it can read B. And it gets that B is 2,000, right? Oh, sorry. Yes, indeed. It unlocked A. All right. The next thing that happens is T2 wakes up because A is no longer locked, and it gets its shared lock. The lock manager gives a shared lock to A. A can now, T2. And T2 can, now read A. It gets 950, and it requests a shared lock on B, but it cannot get it because T1 has an exclusive lock on B. Thank you. At which point, thank you very much, T1 can now read B. Good. Increment by 50. Write B back to the database. Unlock it. And guess what? T1 now has no more locks, which means it's done. It can't do anything else in the database. All right, so T1 has essentially committed. And T1 executed a perfectly reasonable single user transaction. It decremented 50 from checking, and it put 50 in savings, right? Everything T1 did was totally consistent and fine. Did T2 do anything of interest before T1? T2 actually didn't do anything at all. It managed to read A, but A was already all good by the time it read it, right? So the serial schedule this will be equivalent to is clearly T1 goes first, T2 goes second. Question?
Yeah, so how does each transaction know when the lock is dropping off? Like, is it like pull it or
Good question. How do these transactions know that they got the lock and wake up, keep moving? We'll do that actually in a slide or two. So hold that thought. Hold that thought. And you might want to ask again because I'm not sure how explicit the slide is. Maybe not as explicit as you want. So we'll get back to that in a sec. Just let's finish out this example. In the last case now, T2 is going to go ahead and wake up because the lock on B has now been acquired that it was requesting. It has a shared lock on B. And it's going to unlock A. So it can no longer acquire any new locks. It's going to read B and unlock B because it's done with it. And just for fun, it's going to print to the screen A plus B, and it's going to add up to 3,000 as we expected. So that's good, all right? T1 was an update transaction. T2 was a reading transaction, and they happened in an order in which T1 went before T2, essentially, even though the reads were somewhat interleaved. Okay, pretty good. Thank you. I think there's one more. Let's see. There's one more. Okay, things happen in a slightly different order here, but let's maybe not work through the details. What's different here? Let's just toggle. In this case, T2's read was interleaved between T1's write of A and T1's dealing with B. Here, T1 went essentially all at once. The effect is the same, right? In both cases, it's conflict equivalent to a serial schedule of T1 going first and T2 going second. Okay? So I think that's really the only thing to emphasize on these two things. All right, this will also give us a correct output as if T1 went first and T2 went second. All right, how about thanks for our volunteer? Excellent work. Okay, so hopefully this just gives you at least a tangible sense of two-phase locking in action. You can see that things kind of get ordered in a very deliberate way. I mean, when you have lots of conflicts, it feels pretty much like a serial schedule. If all your reads and writes are to the same object, it essentially is a serial schedule, right? Because you queue up for locks for that single object. But what it does is it detects when people are working on different objects, and it lets them go in parallel, right? And it lets you get arbitrary orders of reads and writes on those unrelated objects, which is exactly what we want in conflict serializability. So it's a very sort of literal implementation in some ways of conflict serializability. Okay, just to, bend your head a little bit, here's a Venn diagram of the schedules that are permitted by different definitions of serializability. So there's the space of all possible schedules, right? You have a set of transactions, they have a set of actions. There's all the permutations of those actions defines all the schedules. Make sense? So the list of all schedules is the permutation of all the actions across all the transactions in your workload. A subset of all the schedules are the schedules that avoid cascading abort. Okay? A separate subset of the schedules are the view serializable schedules. The conflict serializable schedules, as we know, are a subset of the view serializable schedules because view serializable is conflict serializable plus it deals with these blind write cases, right? The serial schedules are obviously a subset of the conflict serializable schedules because they are conflict serializable to themselves, okay? But avoid cascading aborts is sort of a crosscut. And then, which schedules does strict 2PL allow? Some of the conflict serializable schedules. Actually, it's not entirely equivalent. And you might want to think about conflict serializable schedules that 2PL prevents. All right, I'll let you do that in your copious spare time. Okay? So much for what can be done and one way to do it, right? We talked about some things that could be done, some classes of schedules, and we talked about two-phase locking as a good concrete way to implement an acceptable set of schedules. So now let's dig one level deeper into implementation and answer the question that was asked just a moment ago on how actually does this lock management get implemented, right? It isn't magic. It's just a protocol. And somewhere in the system, we have to keep track of all these locks. And we have to use that place we keep track of locks correctly to respect the lock protocol. So there's this module in most database systems called the lock manager. The lock manager maintains one data structure, which is a hash table, which is keyed on the names of the objects being locked. It says being locks, but it should say being locked. It's pretty confusing the way it's written. So in the previous screen, we were locking things called A and B and so on. Those are the keys of this hash table. All right? And the lock manager is going to keep an entry for each currently held lock. So if you lock something called B, there will be an entry for B. All right? The lock manager doesn't need to know what the names of all the things are in advance. It's just a hash table. All right? So if you define a new data item in the database, we could lock that too. All right, what is the entry, though? When it's keyed on the name, what do we store in there? What's the value, so to speak, in this hash table? Well, it's going to contain the set of transactions that are currently granted access to the lock. Remember, in a shared lock, there may be many transactions that have been granted access. All right, so there's a set of granted transactions, sometimes called the granted group. Right? It's the group of transactions that currently have been granted access to this lock. The type of the lock that's held, is it shared or is it exclusive? And then, for those guys who are waiting, we need a wait queue, and that's where we'll keep it. We'll keep it right there in the hash table. All right, so it's the names of the transactions in order of arrival, probably. All right, waiting for that lock. This didn't quite answer your question. This is where all the state of the lock manager is kept and how it's kept. When a lock request arrives, you look in the hash table, you being the lock manager. Is there any other transaction with a conflicting lock? The answer is no. Then you put the requester into the granted set, and you let them proceed. So if you think of your lock manager as a function call, I would like a lock, please. This would be the point where the thing would just return and say, go for it, right? It would have put your state into the lock table, and it would have just returned control to your thread. All right? However, if the transaction is not able to acquire the lock, it gets put on a wait queue. And there's different ways to implement this now, depending on how you implement your database system. So this has everything to do with how you get multiple transactions assigned to threads in the database. And it's not in the slides because it's kind of fussy. But here's one way to think about it. Suppose you have a thread per transaction. This is one way that databases get implemented. Not the only way, but one way. Then, this is pretty straightforward. When you get put in the lock queue, you are a thread. And the thread scheduler is told that you can't run right now because you're in the lock queue. And that's it, right? You made a function call to the lock manager that said, please grant me this lock. And that function call just hasn't returned yet. Okay? When you get granted the lock, the function call returns. It says, sure, you have the lock. And you go, cool, I just asked for that, right? Yeah, great. You wake up and you go forward, right? So that's one way to do this. So thread per transaction, this is just like a synchronous call to the lock manager. Another way to do it, though, is you have a single thread, let's say for the entire database, in which case a transaction doesn't have a thread. There's the do stuff thread for the database, right? And when it's in the middle of doing stuff for transaction 1, and transaction 1 says, I would like this lock, and it can't have the lock, then the thread will say, okay, let's put the state of transaction 1 off somewhere in the lock manager, and let's move to another transaction and work on that for a while, right? At which point, when does that transaction 1 get invoked again? Well, at some point, the database thread that's doing stuff is going to unlock something in the lock table and say, well, who could I work on next? Who got access now that I unlocked somebody? And then they would work on that guy, right? These have the same effect. It has all to do with, is threading being done by some JVM or operating system or something like that? Or is threading being done essentially in the head of the guy who wrote the database system? Okay, so it's sort of up to you. And by the way, this isn't a very good way to implement things. Usually you do a single thread per core. So you're actually writing a multi-threaded database engine, but the threads are not per transaction. The threads are per hardware unit of processing. And so you actually have to worry about concurrent threads, which is hard to do. I won't say anything more about this in this class, but if you want, I pointed you earlier to this paper on anatomy of a database system, and the beginning of the paper is entirely about decisions like this. How many threads, how many processes, how do they do that stuff? So you can read more there. But a simple way to think about it right now, since most of you are kind of single-threaded developers, is imagine a transaction as a thread, and you make a synchronous call to the lock manager, and it doesn't return until it can give you the lock. Okay? You can think of the lock manager as being another thread in your system that guards this lock table. I don't think we'll go through the example anymore. What you might want to do is think about, well, let me just draw a picture for you. That's really what the example is for. Maybe it's worth it, at least a little bit. We're going to have a hash table of lock names. And basically what this example is showing you is what happens when you get a lock request. Transaction 1 requests A. Well, then in this hash table, which is the lock table, suddenly we'll have a value for A. What's it going to contain? It's going to contain the granted group of transactions, which is currently T1. It's going to contain the lock mode, which is currently exclusive. And it's going to have a wait queue for A, which is currently empty. Okay? Right? That's what's in the lock table for A. T2 requests a lock on B, so you get a similar thing. You get granted is T2. The mode is S. The wait queue is nobody. And so on. When this guy gets a shared lock, wants a shared lock on A over there, what happens? He says, I'd like a shared lock on A. We look in here. We say, oh, there is a lock on A, and it's in exclusive mode, which means that you, T2, go on the wait queue. Okay? Right? And then that's it. It doesn't return from the call. Meanwhile, T1 reads A, writes A, wants an exclusive lock on B, looks in the hash table. Oh, got to wait for that. Now T2 is waiting here. Or sorry, T1 is waiting here. And we have deadlock, right? Because T1 is waiting for T2 and T2 is waiting for T1. But these are sort of the data structure in the lock table. Okay, I just want to make it very explicit so you see what it looks like. So deadlock can happen. Let's talk about that now. Any questions before we go into deadlock? Any questions about just the lock manager and its operation? Yes. Can both 2PL and strict 2PL have deadlock? Yes, they both can have deadlock. Yeah. Deadlock is one of those funny things that seems sort of cosmic, but really it's not very interesting when you stare at it for a little while. It's just that I've requested one resource and you've requested the other resource, and then we alternate in time, the order of our requests. Right? It's not really all that cosmic at all. It's really pretty simple. All right. The question is, how do you deal with it? Basically, what is a deadlock? A deadlock is a cycle of waiting. I am waiting for you, you are waiting for me. Or I am waiting for Sally, Sally's waiting for Bob, and Bob is waiting for me. Right? Some cycle of waiting. Right? Cycles of waiting are bad. So what are we going to do about it? One thing to do is to prevent deadlocks entirely in your system. We'll talk about this briefly in a minute, but it's non-starter for databases. So there's really only two ways to deal with things, and that's not one of them, okay? But they're usually described as three ways of dealing with deadlocks. Operating systems often like deadlock prevention because it's fast, but it's just not an option for us, and you'll see why in a sec. But the other two options are to avoid deadlocks actively, or to detect them and then resolve them, okay? Some systems don't do any of these things. They just do timeouts. Like if a transaction's waiting around for too long, it's been in the wait queues of some locks for a while, well, you know what? If it waits for too long, just abort it and restart it. So that's a viable thing to do. What might be a problem with it? Say again?
No deadlock can.
Yeah, it could. There could be no deadlock at all. Is that what you said?
Or it could just deadlock.
Oh, it could deadlock again. I see. Yeah, both of those things are true. Good. So one thing that could happen is, you get into a deadlock situation, you abort yourself, and you get into a deadlock situation all over again, and you abort yourself. And the big problem is that, the deadlock is sort of intrinsic, and nothing you're going to do, just kind of restarting is going to fix that until something else happens at a larger time scale. So another way to worry about that, to talk about that, is to say that whatever timeout you pick might not be the right size, so to speak, for what's going on in the system. A smaller side effect to that is, you just might be too conservative. Maybe if you waited a little bit longer, things would have worked out, right? So there's a bunch of dangers with timeouts. If you don't need to use them, you shouldn't, and it's not that hard to do something better than timeouts for deadlock detection. So we will. Before we go on, though, let's talk about deadlock prevention. It's a common technique in operating systems. And the approach is to make sure that resources follow some linear order. Things that you might lock, you have to lock them in an order. And because they're ordered, you can't have cyclic waiting, right? Because you have to acquire the locks in a particular order and release them in a particular order. There's no way that you're waiting for someone who's in front of you and they're waiting for you also, because you never wait for somebody behind you in this order. So, for example, you might say the screen comes before the network card comes before the printer. So if you want to lock the network card, first you have to lock the screen. Right? It's sort of crazy, but with some resources, this isn't crazy. And so you always have to lock things from left to right. And so you can be sure that if you've got the network card, then you can't be waiting for somebody who's got a lock on the screen. All right? So you total order on your resources, and then you can have no cycles of waiting. Why is this problematic for transactions in a database? Why can't we do this? Yeah.
Because you have a very large set of data, like there's to me a giant list.
Okay.
They have unrelated logically.
Nice. We have a giant set of stuff in our database that we might want to lock. Suppose, for example, we want to lock every table. We have table-level locks. Or worse, suppose we want to do row-level locks. So every row in the database has a name. It's tuple ID. We want to lock rows. Well, that's a lot of lock names. What order should they be in? I don't know. Why should the tuples in the employee table come before or after the tuples in the departments table? I don't know. All right, so it's hard to figure out what order you'd impose. Suppose you did impose an order. Suppose we said employee table tuples always come before department tuples. So you have to lock the employee tuples before you lock the department tuples. Why might that be a problem for us? Why might we not like that? We're database folks. Yeah. Okay, things could become slow. Why? I agree. Okay, so then that's an excellent point. So if we start locking individual rows, we might waste a lot of time just running around locking things, right? It's a lot of rows to lock. It's a lot of locks to request. It's a lot of hash table lookups. That is true, and in fact, we're going to try to fix that in a few slides. But that's not a problem with ordering. That's a problem with the granularity of the locks being too fine. So I could solve that by saying, you know what, you're right. Let's just lock tables for a minute. So let's do that. Let's change the question. Suppose I tell you that we're going to lock tables. You have to get a lock on the department's table before you can get a lock on the employee's table. Does that bother us? Maybe it bothers us less now. I don't know. Yeah.
So when we have a when we have an individual transaction, we can't reorder that individual transaction. So like if we acquire the department lock early, then we can't acquire the employee lock later. So that means we have to acquire all the locks at the beginning.
Yeah. So transactions typically, in most systems, are allowed to be interactive. So, you sign on to the computer, you say begin transaction, and you get to decide what order you want to do stuff as a user or as an application program. If we dictate that order in advance, then you'll have to write all your programs. Remember, the database is a programming API, right? You have to write all your programs to think about in advance what are all the things they're going to lock, and then request those locks in the appropriate order. Pre-declaring your locks is kind of a pain in the butt, and in fact, it's not possible if you do interactive applications. Maybe the person accessed the department table and then realized they wanted to access the employee table. You're really going to make them start over? Seems kind of like a drag. Right. So not only do we have all sorts of things that we don't know how to order, the ordering may not make sense to the person using the system. They may want to do things in a different order, and they may be doing it interactively, so they may not even know what order they're going to access things in. So they're exploring the database. They're not going to do it in a particular order. So this just is crazy, okay? And I'm not even sure really why it makes sense in an operating system, but maybe because you hold locks for such a short time, you just burn through all those locks and get out of the way real fast. In any case, this will not work in the database because we can't pre-declare the orders of our locks. Transactions are potentially interactive. So instead what we're going to do, and this is what's typically done in database systems, is two-phase locking with deadlock detection. So what we're just going to do is we're going to maintain a graph of what transactions are waiting for whom. So in particular, it's already here in the lock table, right? I know that T2, because it's in a wait queue for an object that is currently granted to T1, I know that T2 is waiting for T1. I also know there's a wait queue here where T1 is waiting for T2. But we can copy some of this information off on the side and just keep it as a graph. So every time you insert something into here, we'll put an edge in that graph from the thing you inserted here to the thing that's in the granted, right? And if that graph has cycles, well, then you have cyclic waiting and you have a deadlock, right? And then you can pick any node you like on that cycle and you can abort it. And then the deadlock is resolved. And then you could probably want to automatically resubmit that transaction if it was a programmatic transaction. And if it wasn't a programmatic transaction, if it was interactive, you tell the user, oops, start over. It's kind of a drag. All right, so let's do an example real quick, just so you get the flavor of this. We got 4 transactions. Let's march from the left to the right on our locks. T1 gets an S lock on A and an S lock on D. T2 gets an X lock on B. So far, no conflicts. But here we have T1 requesting an S lock on B, and it will conflict with T2. So T1 is waiting for T2. This is not a conflict graph. This is a waits for graph, although they're pretty similar. These are lock requests. These are not reads and writes, right? Just to be clear, this is a different graph than the graph we did for conflict serializability. This is a waits for graph. Okay, we're up to T3 requesting a shared lock on D, which is fine. It's compatible with T1. And T3 also requests a shared lock on C, which is fine. And now T2 requests an exclusive lock on C, which T3 currently holds a shared lock on. So T2 is waiting for T3. T4 comes along and wants an exclusive lock on B, which is currently held by T2. All right? And then T3 requests an exclusive lock on A, which is currently held by T1, and we get a cycle. Okay? So now we've got a deadlock between T1, T2, and T3. All right? Any questions about deadlock detection? It's pretty simple. How many transactions do you think run concurrently in a typical database system? Maybe thousands. It's not like billions. Even if it's millions, that would be a pretty high transaction rate database. This is not a big graph, okay? And cycle detection is not like an exponential algorithm or anything. It's the number of edges, okay? So, this isn't that bad. This is something you can do on the fly in the background every second or something like that. Just look for some cycles in your conflict graph and find the cycles, abort a node, and move on. Empirically, when you study conflict cycles in databases, there are typically 2 or 3 nodes involved in them. They're not long, crazy chains of dependencies. Those don't arise very much because of two-phase locking and because of the way that sort of hotspots in the database tend to lead to waiting on locks. They tend to be like 2 transactions long or 3 transactions long. So they're usually really easy to detect also. Usually detect them quickly, and resolving them is usually not that big a deal. Okay, an alternative, which isn't usually used, but it's worth knowing, an alternative to deadlock detection is called deadlock avoidance. And in this case, transactions are going to abort rather than potentially cause deadlocks. So they're going to proactively cause aborts. All right, so we're going to assign priorities to our transactions based on timestamps, typically the time when they do their first action. So the first time they request a lock, we'll give them a timestamp. Or maybe when they enter the system, we'll give them a timestamp. So suppose that TI wants a lock that TJ holds. So there's 2 possibilities to be considered. And the way you can read these is like if you know these ternary predicates in programming languages, you have a predicate and then a question mark, and then if true, X, if false, Y, right? So the naming schemes are like that. Wait, die. If true, wait. If false, die. Okay? And what's the thing we're testing for? Priority. TI being higher priority than TJ. TI wants the lock. If TI is higher priority than TJ, it waits for TJ to finish. So it waits in that lock queue. If TI is lower priority, so it tries to get in here, but it's lower priority than the granting guy, it just aborts. So that's wait, die. All right. The second scheme is called wound wait. So if TI comes in and has higher priority, it aborts the guy who's got the lock. All right? It aborts the lower priority guy. Otherwise, it waits. So that's wound wait. And because these things are usually based, your priority is usually based on your timestamp, you have higher priority if you're older, right? So let's see how this works. In the first one, wait, die, old people wait, and young people commit suicide, right? If you're a young person and you run into something that has higher priority than you and you're waiting for it, you abort. In the second one, old people kill young people. Otherwise, young people wait. So no matter how you slice it, it's good for old people. Okay? Why would that be? Why would you want to do that in a database system? Why favor the elderly, so to speak? Well, actually, let's answer this question. Important detail, though. If a transaction restarts, make sure it gets the original timestamp. Why? So that you get older over time. All right? If every time you abort, you become a newborn, then you'll be a baby all the time, and you'll never have priority, right? Okay. So if you restart, you get to keep your original timestamp. So you will get older. So why is it good to favor the elderly? Sure.
Because...
Out of respect, damn it.
they're going to die soon.
What's wrong with you people?
Because they're going to finish soon and free up resources.
Ah, very interesting. So one argument, and it is a good one, is that old people are already squatting on all the cash, and you want to get them out of the system and get that inheritance tax and get their goods handed off to the next generation. So the sooner the old people finish with their lives, damn it, right, then the better for the young people. And that's the reason that you might wait for older people, right? You're like, probably just as well to get you done because you're almost done anyway. Okay. But what about this thing about killing yourself? Like old people, if they kill themselves, they don't have any resources. That seems good, right? To be clear, I made this analogy with cash, but you understand what it is in the database, right? If you're an old transaction, you probably have a lot of locks, right? And if you have a lot of locks, then you're blocking out a lot of the system from younger transactions making progress. Another thing, if you're an old person and you've done a lot of work in your life or in your transaction, you've done a lot of writes. If we abort you, we have to undo a lot of work. And then when we restart you, you have to redo a whole lot of work. So there's more work wasted in the system, right? So it's bad to kick people out after they've done a lot of work because that work would be wasted. And it's resources that we all would like, those computing resources, right? Okay. But after all, I think that answered the whole question. I think we covered all the bases. If you kill an old person, all their work was for naught. Right? And all the resources that were spent by society on them, all those IOs, are for naught. Okay? So it's good to get them out of the way. Also, they may be sitting on a lot of locks, and they may be almost done. And the minute they're done, a whole lot of people will be able to go. So lots of good reasons to favor the old. Also because it's nice. Because they raised you, damn it. Okay. So that's deadlock avoidance. Any questions? Which of those is better? Here's a question. Wound wait or wait die? I don't know. I don't think it's well understood. If I remember correctly, I read a paper about this in graduate school, and I think it's one of those like shrug your shoulders, who cares kind of things. I'm not really sure which one is better, and we were always taught to teach both, so I've now taught you both. My job is done. Okay. Sometimes, like, you're a teacher, you're like, I don't know, it's in the book. So this is in the book. I learned it in grad school. People don't implement this. They implement deadlock detection. Again, all this stuff is up for grabs these days. You may very well find yourself inventing a new class of database, and you may decide that deadlock detection is killing you, for example, because your system is running on computers all over the world, and building that waits for graph requires communicating amongst all those computers. Maybe that's bad. So you decide you're going to implement deadlock avoidance, and you're so glad that you learned some textbook stuff from the 70s, even though you didn't know what was the best solution. By the way, had I answered the question, it's probably wrong for the system you're going to build in 5 years anyhow, because the world will change. Right? A lot of these performance trade-offs on close calls, you have to reevaluate them in a new system. So it was good for you to learn this. So there. All right, enough lecturing for today. Next Thursday, we're almost done, by the way, with basic transaction stuff, which we'll finish up next Tuesday. But Thursday of this week, we have a guest lecture. A PhD student from Berkeley, former PhD, I should say, now doctor, Reynolds Shin, who works down at Databricks, which is the Spark company. It's actually down in San Francisco now. He's going to come and talk to you guys about Hadoop and Spark and big data, and he can talk from the front lines. So it should be a lot of fun. All right, take care.